Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And just to sort of introduce myself a little bit, I'm a card-carrying neuroscientist first and foremost, but we dabble in computer vision and machine learning. And I'll tell you a little bit about that work. But the gist of my lab, which is a little bit of a three-ring circus, is that we sort of treat neurobiology as a reverse engineering problem. So on one hand, we study natural systems. On the other hand, we build artificial systems that we try and make work the same way. So that's everything on the natural side for human behavior and functional magnetic resonance imaging. I worked for 5 hard, long years working with monkeys. And then we also work with rats.
And then meanwhile, on the other side, we work with artificial systems, and we work particularly in computer vision and face recognition, in contrast to a lot of computational neuroscience groups that focus on modeling the activity of neurons. We actually try and build systems that really work and try and engage with the computer vision and machine learning field. So basically all of what I do falls into the category of biologically inspired machine learning. And there was a time when this would require justification, that we'd have to explain why it was interesting to look at biology. But nowadays it's not so mysterious. So we have neurons on one hand, which have many connections, and that inspired back in the 80s, and actually with work that extended way before that to build up these neural network models. And then, inspired by the hierarchy of the visual system, where one area projects to the next area to the next area, we've got these sort of hierarchical models, including things like latent, and also this whole big world of deep learning, which has basically taken over everything. So I don't really need to justify anymore, which is it's something of a relief to me, that it's a good idea to look at biology and take something from it and build something. But what I'm going to tell you about today is not that work. So I'm save that for another day, another talk. What I want to talk about is a very, very new line of work in my lab, where instead of just taking inspiration from biology, what we want to ask is, can we actually take the data, the actual data from biology, and bake it into some kind of machine learning system? And that's what I'm calling biologically informed computing. And the reason I call it that is because once you give something a name, then it has a life of its own, and that's generally a good thing for grants and papers and whatnot. So you heard it here first, biologically informed computing. So in truth, all machine learning, or most of machine learning, is biologically informed. And by that, what I mean is, we take an image, if we're doing computer vision, say we want to make a camel detector. I have my camel here. I give it to a brain. It happens to be inside a head. The head can talk. We have somebody, maybe a grad student, maybe a subject, will ground truth that image. And their job is to say, camel. And you're all very good at this. And then that becomes your ground truth annotation. You have another image that's not a camel. In this case, it's a sort of castle-looking thing. And you give it to a human. The human says, not a camel. So this isn't sort of controversial in any way, shape, or form. This is just what we've been doing for a lot of time. We generally don't think about it. And then, traditional supervised learning, again, this is nothing new to this audience. Basically, we have all the camels, we have all the not camels, and we draw a line. We have a function that tells you which is a camel and which is not a camel. So no big deal. So the way we do this is with loss functions. And this is, basically you're just optimizing to create this function. And for an SVM, you'd have hinge loss for the loss function, a well-known loss function. And the key thing is that this is where the human is hiding. The human provided ground truth labels, and that's being used to train your system. And then sort of it's indelibly sort of now marked into your system that there's this sort of biological information that's in there. But what we wanted to ask is, can we squeeze more information out of our subjects, out of the brain, than just these labels? Because if you think about it, a label is sort of the shallowest thing we could possibly get. Just a binary label. Is this a camel, or is this not a camel, or is this a face, or is this does this person have Alzheimer's or not, or whatever? It's just a label. So just like what Paulina was doing, getting sort of more information from the actual biology, we're asking, can we do that in a much broader way for all kinds of different kinds of tasks? And people have done various versions of this. We're certainly not the first people to think that you could put humans sort of more in the loop. So there's a whole field of active learning where you take a human who is again assumed to be sort of an oracle of ground truth, and adds labels, you train an algorithm, and then you query to find examples that you did poorly on, and then you ask humans to label more examples to try and help out. So this kind of human in the loop approach works very well, and it's very effective. At the same time, you can also ask experts to try and codify what they know, take some domain knowledge, and various people have worked on having these sort of expert SVMs where you try and take some sort of idea that, rule of thumb that a human gives you, human expert gives you, and then try and use that to bias the evolution of the training of the SVM. The problem here is that at some level, humans are shockingly bad at knowing how they do things. And if, depending on the domain, it turns out actually a lot of domain experts don't have good rules of thumb. The rules of thumb actually don't usefully inform, though there has been a little bit of progress in this area. But we wanted to do something that was much, much more general. So the intuition for the idea is actually very, very simple. And it's this, that not all examples are created equal. So if we're looking at face detection, this is a widely studied problem. It's a largely unsolved problem. What we can see is that there are some cases that all face detectors are Picasso, iTunes, Viola Jones, whatever, are all gonna get very easily. This is a frontal face that you'd expect this to be an easy example. But the key thing is that not all examples are like that. So if a human were ground truthing this, he would tell us, or she would tell us that there's one here, one here, one here, one here, one here, one here. But this one's considerably harder than that one. The person's in profile, they're slightly blurry. You have this other one which is very blurry. You have this other face where there's clearly a person here, but they're heavily occluded. A human would know that somebody is there, but there might even be ambiguity depending on your instructions, whether you'd label that as a person or not. So the fundamental just idea that we wanted to explore was, could we take advantage of this fact and basically just say, getting easy ones wrong should carry a high penalty. And we shouldn't radically alter our solution to the SVM if we're trying to catch a hard one. So if there's an example that even humans missed, maybe we shouldn't break our necks to get that one. So we can just operationalize all this. And basically what this boils down to is an effort to ask, can we model human performance with the goal of making our classifiers more human-like? Another way to say this is, we'd like our classifiers to make mistakes like humans make mistakes. And it's a little bit counterintuitive that would help. But fundamentally what we're doing is we're piggybacking on a more powerful machine learning system. So even if we haven't seen all the data that the other system has seen, in this case the system we're talking about is a human, we can still benefit from all of their lifetime of experience. We can benefit from the fact that they have a working solution to the problem. And I should say at this point, this doesn't have to be a human that we piggyback on. If we wanted to piggyback on Google or Microsoft or Apple, we could do that using all the same techniques. Anything that's better than us, we can figure out how to make our solution more like theirs, even though we didn't have access to all of their training data, which is kind of a sneaky trick. So in this case, carrying on with faces, we have a situation like this. So if we had faces on this side and non-faces on that side, if we look at some of these examples, maybe we have a misclassification that's a relatively frontal view. This certainly happens. And maybe we have a false positive. We have one that we got, but it was kind of on the edge. What our technique or the intuition would say is, well, maybe we should bias this a little bit. So we would carry a high penalty for getting this easy one wrong, and we'd carry a low penalty for getting this one wrong. So maybe we want to trade it. Maybe we want to sort of tip the hyperplane so that we catch more of the easy ones and don't worry too much about the hard ones. And this, if you've ever done any face detection work, even today in 2014, this is not atypical of what you find in face detection algorithms. So here we have a standard face detector. It's missed this person, probably because she's wearing this headscarf. And then it also has these sort of hilarious, like, it got this guy's arm kind of false positive. So this is still happening even today. Actually, if you go into Google Street View also, it's actually really easy to find images of faces, even though they're required by law to blur out the faces. And the place you usually see them is occluded by the sort of side pillar of the car. So anytime there's an occlusion, you get this beautiful unblurred face, which they get sued for in Europe if they don't catch them. So there's some interest in getting this right. So the problem is that humans are really good. Humans are actually excellent at doing just about any vision task that we care about. And so fundamentally, there's this idea that, well, actually, there's this latent landscape of difficulty that we're not tapping into, and humans are just above it, and that's why we can trust them to be ground truth. But thankfully, we have sort of in neuroscience and psychology for hundreds of years even, people have been developing techniques to bring humans off of ceiling performance and to really interrogate exactly how they're solving a problem and exactly what they know. And this is called psychophysics or psychometrics. And the distinction's a little bit subtle, but people generally use those words to mean the same thing. And the key idea is that if we can bring humans into a regime where we can now interrogate this difficulty landscape, then we can take that information and put it into our kernel machine and get better solutions. So this is what we would call a psychometric function. So this is one of the classic ways to get people off the ceiling. So here we have a face, and basically all we're doing is we're just scrambling the phase. We do a Fourier transform, and then add in a little noise into the phase, and we get this back. And then we can sort of have a nice continuous gradation from something that's very clear or relatively clear to something that's completely devoid of signal. And whenever we have this sort of continuous continuum of difficulty, and when you measure human performance, and then we just have percent correct on the axis here, you can get these very fine sort of judgments of exactly where the threshold is, where they start performing well. And there's a whole field of fitting different functions to this. We can get, if an image is more difficult, it can shift left or right. So if you shift more left, that means you're getting more, you're able to detect the signal even when there's less signal. Shift it the other way, so on and so forth. You can get steeper transitions. You can get more shallow distinctions. And all of these things give you information about what the humans know and what they don't know and how they can do these tasks. If you look at face coherence for humans and for artificial systems, you can see that basically there's no contest. So if we take standard face detectors, like a Viola-Jones detector, this is basically hacked, had a grad student hack Picasa so we could get access to Google's detector. And then face.com, back when they were still in existence, we got numbers from them. They got bought by Facebook. So this is sort of like the antecedent to Facebook's face detection technology. And what we see here is as the image gets less and less coherent, all of the artificial systems crash to chance, whereas the human sort of hangs on way until there's very, very little signal. So even around here at this level of coherence, humans can do this. But basically the artificial face detectors, we're losing it way up there. So humans are awesome at this task. For occluded faces, it's even more interesting. So if we take a face and we just artificially just cover it up with bars, and it doesn't really matter how you do this, and then we just plot the percentage of the area visible. You can see Google hangs on until about 70% of the face is visible, and then you start taking away more than 70% of the face, and it starts falling off a cliff. Face.com, didn't at the time at least tolerate occlusion very much. But if you look at humans, they're able to work with incredibly tiny little slivers of the face. So there's this wide gulf, and the question is, can we use this gulf to figure out how to make our systems better? The other thing that happens when humans ground truth something is if you're measuring carefully, they might also tell you how hard or easy or how representative or a non-representative sample was by how long it took them to make the judgment. So this is sort of in this sort of mode of Native Americans using the whole animal. If we're going to bother to have a human subject sit in front of a computer or a mechanical Turker sit in front of a computer and make these judgments, we might as well measure how long it takes them to make these judgments. And there's a whole field in psychology of taking these reaction time measurements and their distributions and figuring out what that means about the internal processing going on inside their brain. And then finally, the other thing we can do is something called an item response curve. So it turns out not all humans are equally good at all things. So if we rank order our humans by their ability, so in the case of faces, there actually are people who are called super recognizers. This is actually a real thing, apparently. And my collaborator, Ken Nakayama, actually studies these people. So they're really good at faces. And then the other end, you have something called prosopagnosia, where the people who are face blind. So there's this famous book called The Man Who Mistook His Wife for a Hat. Those people have some sort of congenital or acquired defect that makes it impossible for them to, or makes it very difficult for them to recognize faces. And then on a per example basis, we can collect these curves and understand different things about them. So you might be able to tell that a hard image, only your super recognizers are able to get it. An easy image, everybody's able to get. And then you also have these sort of problematic images where there's disagreement for some reason. We get these shallow profile where not everyone's performing the same, and that's also information. So the whole gist of all of this is, can we take this wealth of stuff that psychologists have developed over hundreds of years and figure out a way to put it into machine learning? So that's what we've called perceptual annotation. Again, you have to give things names if you want them to have a real life. And this is work that was primarily done by my postdoc, Walter Shirer, in collaboration with Ken Nakayama in psychology and his grad student, Sam Anthony. So basically what we do, there's many ways you could imagine doing this. There are complicated ways and there's simple ways. As always, it seems like the simple way usually wins. So basically what we do is we just hack the loss function of the SVM, and we just pack in, we just pack in an extra term that penalizes based on consistency by some function with human judgment. So basically the simplest version you can do is just take the accuracy and use that in a lookup table. You've just blown up convexity, but it turns out it doesn't matter. And then you can get, you just basically bake that in. We hack this on top of libsvm, so it runs very fast, converges very effectively. And then this is the basic flow. So we take all of these tasks off of this website called testmybrain.org, which is run by my collaborators. It's basically like a fancier version of Mechanical Turk where the people actually want to be there and actually want to be doing these judgments. We can model the pattern of human errors on a per example basis, and we can use that to inform and constrain a variety of different tasks. And part of the reason I'm showing you face detection is not just because it's an interesting and sort of well-studied problem, but it's also happened to be what the guys in psychology were actually studying at the time. So they were looking at face detection, so they already had a bunch of data, so they gave it to us so we could play with it. And this is Test My Brain. I encourage you to go visit. You can find out if you're a super recognizer or not, or if you have, borderline prosopagnosia. And what people do is they basically just come here because they want to learn about themselves and find out about their brain. So they'll perform hours and hours of psychophysical testing for free, and they'll come back for more. So you can too. So because it's in the world of psychology, we have these sort of funny stimuli. So the way this works is there's two things going on here. One, so we have these faces that are put somewhere on the image randomly. There either is or isn't a face. There are these occluding bars that are randomly put over there. And then the background's kind of this funny looking thing. It's this texture synthesis technique from Eros Simoncelli's lab at NYU. Basically what it's trying to do is match the rough statistics of a face, but have it not be quite a face. So these are very challenging images, and you need to make them challenging like this to get the humans well off ceiling. And then their task is simply to look through these images. They appear one by one, and you ask, is there a face present or not? And then what we do is we have the subjects come in. We present as many of these as they'll stomach. The subjects are responding in their home computers. We're recording accuracy, response time, presentation time, everything about that. And then we can generate all of these psychophysical, psychometric measures that I just told you about. And then basically what we do is we take an existing face detection data set, so normal faces. So the vast majority of our training set is actually normal faces. And then we can pepper in these kind of funny psychophysical images where these can contain little slivers. Presumably they're close to the boundary, close to the margins, but you just sort of pepper in a variable number of those. We've sort of tried all different kinds of variants, and we don't really have a rule of thumb, but if you just pepper in something like a quarter of the images coming from this sort of special set, and they have whatever the regular training set was for your particular benchmark, that seems to work pretty well. And then the goal is then to have these guys influence exactly how you solve your SVM. So we collect the data, we generate these psychophysical measures, and then we come up with this human-weighted loss function, which is basically, again, where we hacked in that extra thing. We have a penalty for margins not consistent with the human data, and then basically we can have solutions then based on that. And just to give you an idea of what the actual data looks like. So if we have those sort of challenging occluded images, this is what they look like in terms of, so on the x-axis here I have the percentage of the face that's visible, ranging from about 30% down to 1%. If we just average all of the examples, so there's many examples at each one of these points, and we can see there's a sort of a fall off in accuracy, which is what you'd expect. As less of the face is available, then the accuracy goes down. But if you actually look at it on an example by example basis, there's actually huge variation around these means. So it's not simply a matter of how much of the face is available. It's also a matter of which parts of the face are available. And what that gets captured in this sort of, this plot, which has lots of data. And then what we can do is, what we're imagining is happening then is that these examples where a lot of the face was available, but subjects still did poorly, or very little of the face was available, but the subjects still did well, are very informative when we put it into this formulation of the perceptual annotated SVM. So, and then of course we need to actually test this on some sort of accepted data set. So we use this face detection data set called FDDB. Suffice to say, it's just a bunch of images taken off the internet. A lot of people report numbers on this data set. And importantly, they're not all frontal faces. there are lots of different views and different amounts of blurriness, and your goal is to try and catch all the faces. And then what we do is we basically just take an existing face detection pipeline, we do it at many scales, loosen it up so we get lots of false positives, then we put a perceptually annotated SVM on top that filter things out, then we have some sort of scoring strategy to avoid having duplicates, and then we get a final result. So there's a couple variants of this, so everything from those synthetic images like I showed you, but then we also took out of another data set of face detection called the AFLW, the Annotated Facial Landmarks in the Wild set. This one turns out to have enough difficult examples because they're real Flickr photos that we can take these images and do perceptual annotation with these as well, and we can pepper each of those in. We can also try different feature vectors, so we're gonna take the images and we're gonna put them through into different feature representations, so we could use just a simple hog histogram-oriented gradients feature representation, but we can also use, this was a bio-inspired feature set that we had around the lab that was previously the best one on a particular face recognition data set called LFW. So this is another one we used. And then finally, we can try different, we can try per item accuracy, but we can also try reaction time and see which ones work better and worse. So the bottom line is, so here I'm just showing you performance across a bunch of different folds. You can see this is the annotated faces and the annotated facial landmarks in the wild, the AFLW data set. These are natural and these are synthetic images. And you can see the performance is at some level. And then if this is with hinge loss, but if we add in this human-weighted loss, we get a substantial boost in performance. And we're getting pretty close to the ceiling, so any kind of jump, this is on the order of 4 or 5% boost for using this human-weighted loss. So a substantial gain. And then if this works irrespective of whichever feature representation you use. So for hog, you get a nice boost. For our bio-inspired features, which worked well on faces before and not surprisingly work well in this context as well, we also still get a nice boost. So we can vary the features. And then we can also vary which psychometric variable we use. So we can use accuracy to get this boost. And it turns out if we use reaction time, we get exactly the same boost. So we're just using how quickly the person responded to each one of these images. And that gives us a nice solid boost. And then if we just look at the ROC curves, you can see we get this healthy boost relative to a default when we don't do this human-weighted loss. And then at the time, at least, when we published this, which was just a couple months, actually it was just a couple months ago, this also was the best system available. So if we look at the sort of standard benchmark here, are a variety of different techniques in the field. And you can see one of the biggest strengths of our approach is it goes down for very, very low false positive rates. We still get very, very high accuracy. And then it's also worth noting that it's built on top of this Viola-Jones detector. So we're getting a huge boost over doing just regular Viola-Jones. And it should also be noted that you could do this on top of any other sort of underlying face detector. So we think we can get good boosts out of other ones. There's another metric that counts not just how, whether you caught the face or not, but how good the match was, how much you overlapped with it. And there, at least at the time, we were sort of even more dominant. So it's not only getting detections, it's also getting very good detections. And this just gives you some, sort of a picture of what it looks like. So on the left, we have the detector. It's sort of a standard detector that it's built on. You can see it's missing a lot of the faces. But because we're using something that's sort of, relying on the fact that using humans to look at, to learn more about some occluded faces and things like that, you can see it's actually catching quite a few more. And then, not exactly for fun, but for out of interest, there was this recent Boston Marathon bombing, and one of the big stories that came out of that was that facial recognition software just didn't help. It wasn't useful. So we ended up looking at those images in some detail that were available. And one of the things that's sort of bad about existing face detection and recognition pipelines is oftentimes you lose the face. You're not even detecting the face. So if that's the first step of your pipeline, you've lost the whole thing. And this was all crowd imagery that they were using to try and solve the crime, and it wasn't helpful. They weren't catching a lot of these faces. But when you run our stuff on it, actually we have a significant number of detections that the other ones missed. So here's some other detections that were missed. And then if we do perceptual annotation here, we can actually catch him and profile as he's running away. So we're missing a lot of faces. We have a lot of false positives, but overall having sort of this increase in accuracy is a big deal if that's the first step in your pipeline. One of the things that's also true in this sort of regime is that a lot of the data is very poor. You have video, low quality video, you have ghosting and things like that, and standard detectors don't do very well. But for whatever reason, our perceptually annotated detectors actually can catch a lot of these examples in spite of very, very low quality. So that's sort of the overall overview of what we've done so far as a proof of concept that you can take a lot more information from humans and bake it into a machine learning system. Going forward, we're taking this in an even more sort of sci-fi direction. So we've been collaborating with Jack Gallant at Berkeley, who does functional magnetic resonance imaging of human brains while humans are looking at visual stimuli. So for every image the subject sees, they image the brain, and we have a vector basically of the activity across their brain. And what we're working on now is trying to figure out, can we use that, the embedding of that space, this high-dimensional space of sort of the brain activity, can we use that in a similar way that we used it, the human performance data to bias and constrain and regularize our solutions in the SVM or in another kind of classifier. We also are looking at cellular resolution data, so this is actually an instrument that we have in my own lab and the other side of my lab. So this is a laser scanning 2-photon microscope. Basically, we shoot a laser into brains and then get virally infected, genetically encoded fluorophores to light up in response to activity. Sounds kind of sci-fi, it kind of is. And then we can get cell-by-cell activity. And again, we can look at the sort of vector space embedding of each stimulus in some brain space, and then we can basically try and build solutions that work the same way. And since I'm done with time, I'm just going to skip ahead a little bit and just thank everyone in my lab, particularly Walter Shire, whose work this was, and then, of course, everyone who's supported our work. And I'd like to thank you guys all for your kind attention.
So I'm just trying to understand where the gain is coming from. So it seems like when you strip everything away, rather than having the training set being a bunch of ones and zeros, the face of zero wasn't there, you're having almost like a voting scheme based on the human annotation. Is that basically it, that you're giving it sort of fuzzier type?
Not exactly. So what we're doing is for a subset of, so we're peppering in as many perceptually annotated examples as we can manage. That's smaller than the full training set. So not every example in the training set has this extra information. One way to think about it is as a regularization term. So we're penalizing solutions that are less human-like, just the same way as you might penalize solutions that are more complex. One of the interesting outcomes of this, which what we didn't expect, is that we have many fewer support vectors for the human-weighted loss than we do for a hinge loss. So the solutions are sparser. They're simpler. We don't know why that's true. Something about if you rely on the humans to sort of give you some idea of which ones were easy and hard, you get sort of less crazy solutions to the problem. And we think that also helps. But we're just putting bias terms in there to say, for a subset of the examples, how painful should it be to get this one right or get this one wrong? Does that make sense?
When you actually do the evaluation, that doesn't come in, either it's right or it's wrong. There isn't any, when you're doing the evaluation.
So when we do,
that doesn't come into play. So I don't know. I don't totally get how it's helping you when you do the sort of.
Yeah, sure.
Yeah. So it looks like you just adjusted the margin for certain examples based on how hard it was for humans to annotate. So I was wondering why you chose to do that instead of just importance weighting the examples, which is another way to do it, right? To multiply it by some weight.
Yeah, I mean, that's, you could certainly, there's lots of different ways you could implement this. We need to have, I mean, it is analogous in many ways to importance sampling. We're weighting the examples based on any number of different measures. The one thing is that you can also vary what the sort of mapping function is to individual weighting. So different measures, reaction time, we're going to have some sort of normalized weighting for that versus accuracy versus item response versus slope of psychometric curve and all these other things. But the key thing is that this is a mechanism for deciding what's important and what's not.
I was wondering the intuition as to why you use sort of the additive thing versus a multiplicative weighting.
Yeah, I mean, they both work. I mean, it doesn't really matter.
So you mentioned that about a quarter of the training set was these text and then included sorts of synthetic images. So I almost wonder, why not 100%? How valuable are those images, and why? What happens? Is there some hilarious outcome?
Yeah. So there's two. What was that? Oh, right, sorry. So asking why did we only use about a quarter of the examples? Why didn't we just have all of the examples be perceptually annotated? There's two reasons for that. One is there's a resource limitation, so you can only perceptually annotate. They're expensive to perceptually annotate. We have tens of thousands of subjects looking at these images, so you can't do all of them necessarily, though you could in theory, in which case then we'd expect it would work better, but it's sort of a question of how you allocate that. In the case of the Simoncelli textures, those synthetic ones, if you just train on those, you get less good performance on something normal because the classifier's never seen what normal looks like. So you're sort of in this weird regime where you're off in this corner, which is a valid corner of space, but you don't want to spend all of, only have training data from this weird corner of space. But if you have some, the vast majority of the data tells you sort of what the basic lay of the land is, and then you're using this funny little corner to help tweak things, that's important. So for the AFLW data, where they're actually just examples from the real world, those are sort of safer to have larger fractions.
Why don't we do one last question while next speaker says that?
Yep.
Any insight when humans are taking longer to recognize an image, what's going on, and how you model that?
Yeah, so the people in psychology have come up with all kinds of theories, and that's sort of like the whole game in reaction time studies. So sometimes people think about multiple processes happening. Sometimes people think about you have to have some sort of inference process that's sort of percolating to a solution. The short answer is nobody really knows. Yeah, it's just giving us a readout, which actually turns out to be equivalent to the readout of the accuracy across a large population. So we were hoping that putting the two together would give us an extra boost, but it turns out not to be true. The reaction time is giving you the same information as a population accuracy is. Great, thank you.